And welcome to this with Lady Ada.
Hello! Thank you for making me magically appear. We got
Yeah.
a fun Monday stream we could do, some stuff I've been working on over the weekend. There was Solar Eclipse Day.
Yeah, there was light,
There was light,
and we were together.
and then there was darkness.
And then there was darkness. And then the darkness went away, and the only thing that remained afterwards was the light and us.
Okay,
I'll play a video at the end.
Very intense. Alright, yeah, we had fun. We went on the roof. We had the
Yeah.
glasses. That did you order those a while ago? Or?
Colin got me 2 sets of America flag glasses.
Good.
Go America. It's our America. And then a bunch of people got glasses from the public library, Warby Parker, because we're in New York and they were handing them out everywhere.
Yeah.
And we'll play a little video at the end. It was fun. We were the most prepared people in our building.
That is very true.
Yeah.
Like, we had glasses,
we had protractors,
viewers.
and we had contraptions.
We had holes punched in boxes.
Yeah. We did science.
Okay, so yeah, we had a good time.
Yeah.
And now we're gonna go do some electronics.
Yeah.
So I thought I'd show just what we were. Let's pretty fast. I'd show what we're working on.
First up, though.
Yeah.
All chats are here. All chats are here. 24/7, 365 now. If you see this on any type of online streaming platform, all the chats are here. This is where we see everything.
Yeah, we can't keep track of Twitch and YouTube.
I can prove it.
And, yeah.
Hi, everybody.
Oh, so now you have that hooked up to a button. You got this cool button thing. Phil bought this really cool button thing.
Yeah, we're gonna make a better open source version eventually, but this is giving us ideas. I'll show it at the end of the show, maybe.
Yeah. Okay.
Okay. So
Well,
where are we starting?
Okay, so I thought I would actually let's go to the computer.
Yep.
I'm gonna learn. So one of the things that I do all the time is work on testers, because that's kind of what I do. And for a really long time, I was using my AVR. I had this AVR programmer, like this standalone AVR chip programmer. So I've used this for a very long time, and the code here, it's kind of it's a neat idea. Basically, in AVR, so I was like 6 years old. The AVR itself bit bang programs another AVR, and so it's very, very fast. And you can use it an AVR programmer like an ICE or a USB Teeny or ISP or whatever. But just having a computer involved takes a long time. There's all these USB transactions, and there's overhead, and it's just not as fast as if you directly write a chip. And so a long time ago, I moved from, about 6 years ago, I moved from having a AVR programmer connected to a computer to program chips. And I basically redid all of our programmers to use an AVR with an AVR. So you have like a Metro, and then on top I'd have like a shield, and then the chip would plug into it. So you can like, see here I have like a video.
Hey everybody, Arduino.
So this is like the programmer. So this was for programming Arduino chips, for example. You can see it says like Arduino, and I'll turn this down. And then when you put the chip in, see if I can grab a chip and slot it in. Hey, past me, go faster. Okay, put the chip in. You push it down, and you press a button, and it takes like 1 second to program the bootloader. It's very, very fast because you don't have all this overhead of reading a file. Actually, the flash image is stored in the memory of the host programmer, and this actually made programming things really fast. So, like for example, our feather line, the 32U4 based feathers, we program very, very fast because they're programmed from like a Metro or something, and like they go super quick. Like you can basically program and test a feather 32U4 or one of our 32U4 based boards in like 5 seconds. Whereas if you had a computer do it, it would take like 15 to 20, which that actually makes a big difference.
I have 2 things to point out.
Yeah.
1, that's Adafruit Apartment Company. 2, you still wear that same shirt all the time.
No, I don't know what my Reverie shirt is.
No, it's in the laundry.
Is it?
Yeah. No, I saw it the other day.
I haven't seen this Reverie shirt. I don't actually know what happened to my Reverie shirt. This
Yeah.
was a goth club in Boston.
Yeah.
I used to go to. It was at an Irish bar.
You know,
here.
I might wear it to sleep once in a while.
Maybe that's where it went.
Yeah.
You wear it.
Yeah.
But yeah, so you can see like I'm like testing stuff on my own desk. But so this is how I would do AVR programming. So that's really good. The problem is that as we've gone to more advanced chips, we're using chips like Cortex M0s M3s and 4s, and those chips don't get programmed the same way. Like the AVR is actually programmed very easily. They use an SPI protocol, and it's like really well documented and very simple. And Atmel came up with it, but it's a simple protocol. It's easy to implement. So you can do it in C code on an Arduino, and also it's SPI, so it's really easy. It's basically just you send an 8-bit command, and then you send the 8-bit address and the 8-bit data, and then I think there's like a checksum bit or byte or something. Whereas for the Cortex series, the Cortex M0s, M3s, M4s use a different programming system called SWD, Single Wire Debug, which is a simplified version of JTAG. And SWD is actually kind of interesting because it's not SPI. It uses, let me see if I can find like a good document that shows how it works. But basically with SWD, okay, so here you go. This is like the diagram of it. So SWD, it's not like SPI where there's a clock and then data out and data in, right? Because like the ISP header for Atmel is like it's mostly MISO, and S clock it really is SPI. This uses one clock line, which is always from host to target, but the data is actually kind of weird. Like you send, so 1, 2, 3, 4, 5, 6, 7, 8 bits from the driver to the target, and then there is a turnaround bit where like you tri-state and you switch, and then the target actually responds back 3 bits, and then you send another turnaround bit, and then you send 32 bits of data, 1 parity bit, so 33 bits. So you can see this is like, there's like 3 bits and there's turnaround, there's 33. It's not friendly, it's not SPI, it's a much more complicated protocol, but it's very compact. Right? The reason they did this is they want to make it as fast and compact as possible, because when you're programming these gigantic chips, you want to make it like super speedy to go back and forth. So this is, how to write data, and then when you want to read data, I think it's very similar, except that 33 bits comes the other direction. So this is how SWD works. So it's called SW clock, SW data, IO, because it's bidirectional. And we're working on a couple things here at Adafruit. One of them is called Stemma, where we're using, and Seesaw, where we're using the SAMD09 chip as kind of like an interface chip. And basically I wanted to be able to program SAMD09 chips, which are not very big. They're like 16K of flash, but they need SWD, and you need to be able to program them. I want to be able to program them in like a second or two. I couldn't have like OpenOCD and then there's like a JTAG thing or JLink. It's like such confusing. So I was like, well, look, I don't want to do that. I want to have it be like we do with the AVRs, where it's all contained. There's no Raspberry Pi or OpenOCD or CMSIS DAP. It's all in one. And so we actually started looking at this in detail, and this was something I assigned to Dean, who is helping me out at Adafruit. And I said, hey, check this out. There's this fellow, Atarov, he's at Atmel actually, and he wrote a CMSIS DAP firmware for the SAMD21. So basically turns a SAMD21 into a CMSIS DAP tool. Like usually, like you'd use this as your CMSIS DAP tool, like a JLink, and this would connect your computer, and then this.
The overhead or something?
Yeah, sure.
We have one.
Yeah, I got an overhead.
Oh, yeah.
So
focus.
Something like the JLink can do it. You can see it says SWD, and then it has a lot of pins because it can do JTAG also. And then on the other side, there's this little adapter, and then this would be what you program. But it just gets like clunky and complicated. And this is USB, so you need a computer. So we were like, okay, let's. What we can do is take the CMSIS DAP code that he wrote for the SAMD21, and then turn that into Arduino, but then also take the command, like a program that runs CMSIS DAP on like a command line program, like on Linux or DOS or Mac or whatever, and then combine both of them together so that you have both the hardware interface and the software control, but you just do them together, and that should allow you to program a Cortex M0 using any microcontroller. And what's interesting is I know that people have done this. Like I know that Scanlime did this because her MK20 programmer for the Fade Candy is another, I think it's like another Fade Candy, or is it Teensy? So I know that she got this working. And I know that Paul Stoffergen got something like this working because I believe the little chip on the Teensy is a SWD programmer that like on the fly programs in the bootloader into the chip. But I couldn't find any code online for this, and especially ones that would support the SAMD series. So I was like, well, let's just start from, first elements and make this. So we released a new library called Adafruit DAP, and this is almost all just the Adafruit code, and Dean basically wrapped it and made it really like nice and elegant. We have example code that basically you define which pins are your SWD clock and data lines. So those are the lines that go from the Arduino compatible chip to your Cortex M0. And then the firmware file is actually stored on SD cards. And the reason we do that is because it's like, binary files are pretty easy to read. It's fast enough. And these Cortex chips often have like a megabyte of flash or, hundreds of Ks of flash. So it's easier to just stick it on an SD card and just have it there. And then you can just run the command. So you can, start the DAP communication and then configure it and, set the link and then convert to SWD. We kind of basically just wrap everything into a nice C++ library. And it'll tell you what target it found, and then it can program it. And then I took it like a step further. And so to make it easier for me while I'm doing like, debug and test, I made a little parser program. So, oh wait, hold on. I'm going to do that. So I have a test text program. So this is the commands. It's on the SD card text file, and then the programmer reads this and it tells it what to do. So this should make it easier for me to deploy multiple different programmers. I just change what the text file says. So for example, this one is for the Feather M0 Basic. I tell it what chip I'm using. And then, you can send a read command. It will read the firmware off for you. Or you can do this, which is just erase, program, then verify, check the serial test output, and then program in a blink program, verify it, and then finally check the USB enumeration. So let's try this out on my tester. So it can go to the overhead. I'll show off the programmer. So this is the original version. So I used an Arduino 0, and then I just wired up this sort of like SWD breakout and then a micro SD card holder. But this is a little bit more compact. It's still an Arduino 0 underneath, which I'm using as the target, the host, and then the target is this Feather M0, and this is the SD card where I store the firmware and commands. And then I added a couple things. I added a NeoPixel here, although it's not working yet, and a couple of breakouts and like a piezo and stuff. And then this is connected to the USB on the go port. So this allows it to test that the USB enumerated. And then let's run this. So let's start up Arduino, and I'll show the
you were
code.
telling me something today about Arduino. They updated the thing so Circuit Playground would work.
Yeah, they did, but I didn't have a chance to check it out.
So we gotta test that?
Yeah, I gotta do that, but I haven't had a chance yet. So this is flash from SD. So this is the example code. So let's try programming this. So you upload the code once, but then you never have to, once it's programmed into the target, then you can disconnect it from the computer and then just we press the button. Every time you press the button, it reprograms your chip for you. So this is very, very handy if you're programming a lot of chips. And there's, JLake makes a standalone programmer, and of course it's, does every chip known to man, and it's like amazing and it's wonderful, but it's like $800. So what's nice about this is it's like $20. It's very easy and simple. So let's open up the terminal. So so it starts, it initializes the card. It says, okay, fine, I found the SD card. And then it says, okay, this is the name of the adapter. It identifies the target. So it says, okay, I found the SAMD21, and it's got 256K of flash and how many pages. So, if you want to check that you've got the right chip. It erases it and it programs it. So it programs it with the Blink, Sketch, and a bootloader. And it's really fast. So let's start again so you can see how fast it is.
You want to go to the overhead? What do you want to do? You want me to switch from computer to overhead like this? I can switch back and forth.
Okay, no,
look at me, look at me, look at me.
So I program it and then it does it. It takes about like 2 seconds, 3 seconds. It's very, very fast. I don't think I do a verify step here. I don't remember. I think I actually skipped the verify step because it pretty much,
Yeah.
if you've managed to connect to it, it's
as someone
really fun.
pointed out in the chat, love that you build the tools that you need. Yeah, we do this all the time. And then once we build tools, we, like our testers, we put them in the store. And one of the things that I like to watch Lady Ada do is testing stuff takes forever, but we're getting really fast at it.
Well, I want to put like Trinket M0s and Gem M0s and sell a lot of them. I want to give them away for free, but I can't do that if it takes 30 seconds to test. And so
it's not out yet. Don't ask. We're going to give away a ton of trinkets and gems for free.
Yeah, but like to do that, I have to make it to program the Trinket Classic. The at ATtiny85 Trinket only takes like 2 seconds or something. It's super fast. Maybe 3 seconds. So I have to make it that fast. I have to make it like trivially easy. Do
you want to do questions at the end or during this?
I can do some questions right now.
Okay.
Let me upload my.
Here's a question. How is this different than when we like flashed ESP8266 or in MicroPython?
Well, that's actually, it has a built-in bootloader, but we actually don't flash the ESP. We get it with Lua, and we kind of ship it with Lua because we figure, this is what people want to use, and then they can load whatever. This is just burning, like this is an empty chip. And also the bootloader for the ESP, it's not that fast, right? Because it goes over serial, whereas this is much faster.
Oh, I'll answer one question. Drew, if you want to buy gems in bulk, just email PT to Adafruit. Because we can do it, but like right now, I have to just figure out how many we can do, so just email me and we'll figure it out.
Okay. So I'm now uploading my my version that reads from the SD card. So this one just, it basically parses out all the commands and then it does different things. So like, if it gets different commands, like for example, if it gets the command erase, it'll erase the target. If you get program, it'll parse out the file name from the text file and it'll program it. Verify, same thing. So let's go here and run this. So this is a slightly longer program, so it takes a little time. But it still took only about 7.8 seconds, so it's pretty fast. You can see it's parsing different commands. Right now I don't do anything with the PID command or the feather and the name command, but eventually I'll check that the chip and the target are the same. But programming the firmware takes about 1.6 seconds. Verifying it takes 1.4 seconds. And then I do the test. And now, I basically connect to the chip and I check that it does the GPIO test. That takes 1 second. And then I program in the final firmware, and that takes a second, and I verify it, which takes about 1 second. So it's very fast. And then, but it's not really fast. So the only problem is that this is fine for basic feather testing. But then if I change this program to be like the Trinket program, so let's go to...
This is a question.
Yeah.
Okay, what would stop you from building a programmer MUX so you could load a bunch at once?
Nothing. You absolutely can. I just would rather have multiple programmers that do one thing than one program that does a lot. But some people like to do that, which is, I get it, it's fine. Okay, so next step, let's try programming in CircuitPython. So CircuitPython is a huge program because it's like the entire CircuitPython interpreter, and it also comes with the USB drive built in. So what I did is I set up a CircuitPython on this feather, and then I sucked the firmware off using the read command, and then I'm going to burn it back on. But this file, in comparison, the other programs were about 30K max of firmware, and this is 230K. So it does make a big difference in the speed. So this time I will press reset. So now it's going to still perform the same test, but instead of the blink sketch, it's going to program in CircuitPython. So you can see it's like taking a while. It's like programming a lot of data. So it takes 13 seconds to program, which is a little too long. Actually, on the on the current tester we use, which programs CircuitPython on a trinket using a Raspberry Pi, it only takes about 12 seconds to program and verify. Whereas this one takes 30 seconds, so it takes 2 times longer through the CircuitPython code. And then if you go to the oscilloscope, we can see why. This is the data. So it's about, I mean, it's not perfect square waves, but it's about 700 kilohertz to the bit clock for sending and receiving data over SWD. Which is fast, but it's not as fast as it could be. For the JTAG, when you use the J-Link, the J-Link to program the Cortex M0, it goes at 4 megahertz. But the problem is actually just because there's it's not, I can't use a peripheral because it's this weird bit bangy, not 8-bit, it's not SPI, I can't take advantage of I2S or SPI or I2C to bang out these bits. I have to do each one because there's these turnaround and it's 3 bits. It's just so weird. So instead of that, I actually have to read and write every bit. And even though I went through and really tweaked out the GPIO to be the super fast GPIO, I can't get it faster than 700 megahertz. I started with 300. And then I just started optimizing away, but I couldn't get it past 700 kilohertz. But I want to do 4 megahertz because I think 4 megahertz. If the bulk of the time is programming these chips, and it is, if I can go from 700 kilohertz to 4 megahertz, that's 5 times faster, right? A little bit more, 5 to 6 times faster, and so that'll cut my time from about 30 seconds. To 5 or 6 seconds, and which is about as fast as what you get from the Raspberry Pi, so that makes sense. The Raspberry Pi does it at max speed. So I was gonna do maybe a teensy 3.6. That's kind of my next bet. Let me show that on the overhead. So this has the SD card built in, which is kind of nice, but most importantly, it has a USB host, and it runs at 180 megahertz. So I don't need that many GPIO. I only need 5 GPIO, but I want it to run as fast as possible, and I want that extra USB host for the enumeration testing. So I think it'll be good. I think I'll try doing that. This is fine for the Feather, but for the Trinket, I'm going to try just checking to make sure the code works on this. It should. There's no real... there's nothing really special about the SWD code. It's just digital writes and reads. Get it working on this, and then look at the scope, get it working at 4 megahertz, and then seeing how fast I can write that CircuitPython code at the maximum speed. And hopefully if I can get it to 6 seconds, that'd be actually really nice. That's I guess that's my lower bound for how fast I can make it. But even 7 or 8 seconds would be really good. Yeah. And also there's no Raspberry Pi, which is good because it adds complexity, having Linux. Right?
Okay, so in theory, you can put a CircuitPython on stock Feather M0 right now.
Yeah. You can. We have releases for the Feather M0 line.
Okay. What else do you want to show?
That's it. You want to show this cat book?
Oh yeah, so shout out to Mosho. He was reading this to his cats, and I bought it. It's a real book. I didn't think it was real. And it's a Star Trek cat book. And what's cool is the cats are kind of close to the characters. Can you skip to the Scotty page where Scotty the cat's drinking?
I like how I like this one where they're
You like Dr. Cat?
Dr.
Pounds. Yeah. Yeah, this is contract. This is a real book. This is neat because...
What is this? You said...
Okay, so they went back in time. This is a really good original Star Trek episode. And, Spock had a hat because he has to cover his ears.
Ah.
Yeah. And this one is I understand you. I feel your pain.
Yeah.
And what's neat is there's one...
I think it's fighting cats.
Yeah, there's one... Yeah, there's the green cat. And there's a Star Trek where the cats... Well, I'm sorry, where the regular Star Trek people are dealing with dogs with horns, and that's in there too. Dun, 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 dun. Yeah.
Guess Spot Guts has that long nose.
Yeah. They should turn this into a show.
This would be a great show.
Yeah. Anyways, cat's beaming down. Cat's doing all sorts of stuff. This is real.
I don't know where this
This is real. This is happening.
This is weird.
Yeah. Yeah. Keep going. Keep going. Keep going. Keep going. Okay. Yeah. Look. 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 Hold it up. Look. Drinky cat. Meow. So, anyways, and then, like it's one of the Scottish fold cats. Kind of nice. And then there's if you
Who's
skip,
this? Is this a con or something?
I don't know. I have to look. I can't see through the overhead. But yeah, look at this. They're just like, hey, there's these dogs that were in there too, and the cat's like, what is going on? It looks like MOSFET.
What's going on?
Yeah.
Tribbles.
This is great. Well, I do this to MOSFET all the time. Yeah.
They're climbing all over the place. I like how their outfits have little like
Yeah.
slots for their tails.
Yeah, well.
There you go. Dun dun dun. Live
Yeah.
long and prosper. So that's that.
That's cat trick. Okay.
Good. All right. Pick up this book. All right. Did you want to show something else?
Yeah.
Did you want to show your little selector?
Oh, yeah. Well, yeah, I'll do that. Okay. So what I'm going to do is I'm going to pull off the scope cam, and I'm going to show this setup right now because it's working out. It's working out. I was in the Discord partner chat, and I'm like, hey, it's working out. So I figured I'd show this to them. Could you detach that camera so I don't go in front of your camera?
What do you want to?
The scope
This?
cam. Yeah, just no. Can you take the Velcro off? Yeah. And then just hand me the camera.
Okay.
And then like go underneath the wires. Yeah. Okay. So here's what's going on here. This is Wirecast. This is the chat.
Well, meta chat.
Yeah. And then this is the soundboard. I have a soundboard. I don't actually need a soundboard, but I have it all hooked up. I don't have these microphones. And then here's Stream Deck. I'm trying this out right now, and this is how I'm running the show. These are all the different things. So when I go to the chat, like watch this, watch chat, boop, see, chat.
Yeah, it's very neat. What I think
chat.
is interesting about this is they don't use like little TFTs for each.
No, it's one screen underneath.
It's one
Super
TFT
smart.
with a resistive touch screen, and then each
Yeah.
button is just clear, and it just presses it.
Yeah.
So it's like it's kind of obvious and genius, and whoever thought of it was very smart. So we're gonna make something not identical, of course, but with CircuitPython we can make something.
Infinity.
Ooh.
Yeah. And I got these black rocks for a drink.
Yeah.
Anyways. Okay. And then you can see some of the behind the scenes here. This is Lady Ada. There's a green screen. You see how this works? And then we have this is an old iMac that works fine. And then I got a camera here. And then we got a secondary display. This is Qualia. That's our display that we made.
And there's a cat over there.
Yeah. No, I can go around. Okay. And then you'll have to help me out here. So this is behind the computer. This is all the wires.
Yeah.
And then I'll just. Oh, can you look at the screen?
Yeah, there's a cat. Oh, you can totally. Oh, he looks good.
Yeah.
Yeah. His eyes are open and he's kind of like annoyed. Hey. Okay. He looks happy now.
Yeah.
Okay, so it's a cat.
Yeah, and so that's how the show runs. It's a old iMac, a laptop over here to look at stuff, and then a camera, and then here's Desk of Lady Ada from this side. And then on Periscope, this is just a phone. You have to have a phone to activate Periscope.
Yeah.
Yeah, and then here's that little box that kind of does all this.
That's cool. Okay.
Yeah. All right, well, that's the show.
Yeah. 3 minutes.
Yeah. Okay, well, thanks, everybody. We're going to play ourselves out with this cool video that we did today. So I'm going to turn off the... here's the chat. Say hi, everybody.
Hi,
What's
everybody.
in the glass besides rocks? Well, whiskey. S&B, Star Trek, cat book, put over the top. Yeah, that was a good show.
Yes.
Yeah. And then I'm going to turn off the hashtag, and then I'm going to turn you off. Boop, you're gone.
Okay.
And then I'm going to turn the audio off, and then we're going to go to the video.
Okay, bye.
Bye. What's going on? I'm gonna try to do double.
Are you guys together? Can you win a win?
What was that?
Are you guys together with the glasses?
Yeah. Sphere. Yay. Run up another sphere.
Yay, America, look this way. This way.
I don't see the crescent yet.
What's that dark evil thing? Oh no, sorry, that's the Trump Soho. There's right. Okay. So in 2:44 is when it. So in 7 minutes it gets full. Really
I got two. Oh, I see. Not exactly. Yeah, not exactly the same.
Does that